Okay, welcome back. Today we'll have a second lecture on domain decomposition. Last class we talked about non-overlapping domain decomposition, also known as Schur complement methods or iterative substructuring methods. And today we'll talk about another large class of domain decomposition methods called overlapping domain decomposition methods, otherwise known as Schwartz methods. There are a number of books on domain decomposition. For the overlapping case, I'm going to suggest two different books than we used last time. So one is a very recent book published by Siam. And another one is an older book which I think is very clear, but there have been some relatively new developments that this older book doesn't cover, that, which is the reason why we should also look at this newer book. Okay? So like last time, I'm going to start with the differential problem and then look at the algebraic interpretation of these methods expressed in differential form. And as usual, we're going to solve this Poisson problem. So in a domain omega, and we'll use Dirichlet boundary conditions. So on the boundary, we'll have 0 on the boundary of the domain. Okay? And now we're going to have we're going to split the domain into two overlapping regions, okay? And the domain that we're going to use is going to have this weird shape. It's a keyhole shape. So instead of a square or circle, we're going to try to solve this differential equation on this keyhole shape. And historically, Schwartz in 1870 was interested in whether or not solutions of this form existed for boundaries that were not square or rectangular. He only had Fourier methods in order to try to at his disposal, so things were a little bit difficult. And he proposed this alternating Schwartz technique to try to prove the existence of a solution. So in our context, we're going to divide this domain into two parts, two overlapping parts. One part is this circle, and the other part is this rectangle. Okay? So let me call this circle omega 1 and this rectangle omega 2. Okay? And there are some boundaries. There are these internal interfaces. So this interface I'm going to call gamma 2. And this interface I'm going to call gamma 1. So gamma 1 is the part of the circle that is interior to the other subdomain, and vice versa. So now I'll talk about the alternating Schwartz technique. Okay, so given these two subdomains, the idea is to solve the subproblems alternately, the first one in omega 1 and then the second one in omega 2. So this means that we'll do omega 1, then omega 2, then omega 1 again, then omega 2 again. So here's what the algorithm looks like. We're going to start with an initial guess. Let's call the initial guess U0. Okay, so the 0, the superscript 0 is the iteration counter. And we actually only need the solution in the second part. But let's suppose that we have an initial guess in the entire solution. And then we're going to loop like before. So this is very similar to yesterday. Let's say n equals 0, 1, 2 until convergence. Okay, and now I'm going to write down the Dirichlet boundary value problem for the first subdomain. Okay, so for this first subdomain, we're going to try to solve. So in the first subdomain, and it has some boundary conditions. So it has the regular boundary conditions, the boundary conditions from the original problem. So u equals 0 on the boundary of 1, okay, but not including this interface, this blue interface. Okay, and we have u is equal to something. Okay, I won't write that down yet. Whatever value we have of the solution on this boundary. Okay, on boundary 1. So I'm going to write down some iteration counters. I think I'll use pink like before. Okay, so this will be the solution at the first half step. Right? Each iteration includes 2 half steps. First one solving on omega 1, second one solving on omega 2. So I'm going to call this n plus a half. Okay, so the u over here is going to be the u taken at n. And in the very first iteration, n equals 0, so we're talking about the initial value. So this specifies this boundary at the very first iteration. It specifies the boundary value gamma 1 here. Okay, so this is just a very simple Dirichlet boundary value problem, right? We're just trying to solve over this circular region. We have this boundary defined by the original problem and the boundary defined by the gamma 1, which is given by the initial guess. Okay, so now we have the second step. So we're going to try to solve in omega 2, u equals 0 in the boundary of omega 2, but not in this interface gamma 2. And like before, u is going to be equal to some previous u on gamma 2. Okay, and let's call this n plus 1. Okay, n plus 1, n plus 1. And what value of u should we use? We're going to use the value that we computed over here. So this is n plus a half. Okay, so that's this thing over here. So in other words, these two subproblems are done in sequence. They're not done in parallel. This is why it's called alternating. We go from one to the other, and then this is end loop. Okay? So this is the alternating Schwartz method. Let's write some notes. In this overlap region, to be very clear what happens in the overlap region, in the first half step, the solution in the overlap region is the solution for the problem on omega 1. And in the second half step, the solution in the overlap region is overwritten by the solution of the boundary value problem for gamma 2. Okay, so in the overlap region, solution is overwritten. So let me write it over here, because in this, what happens in the second part, solution in overlap region is overwritten. Okay, so this is not a parallel method because it's going from one subdomain to another subdomain. How can we make this a parallel method? So this, I think, is an important question. People did not know how to make this a parallel method until relatively recently, at least not at the level of the differential equation. But if we think about how to make this a parallel method, we would have to solve for the subdomain 1 and subdomain 2 at the same time, right? So that's the obvious thing to do if we want to make this a parallel method. But the question arises, if we solve in the two subdomains at the same time, what should be the solution in the overlap region? So you can think, well, the solution in overlap region, well, let's just call it the average of the two, right? So we solved over here, we solved over here. Let's just put the average in the middle. Okay, so is that a good method? That's a good question. Maybe let's write that down. So how do we make it parallel? So the idea is to solve in both omega 1 and omega 2 at the same time. And then the solution in the overlap region is the average of the two solutions. Okay. So does this work? And how well does it work? Okay, so that's one method. I think that this doesn't work so well. So it never became a good method. But let me describe now a better parallel method. And the better parallel method is, the idea is that you will solve in the first subdomain and in the second subdomain at the same time. Whenever you solve in the first subdomain, you take the solution on the boundary here from the second subdomain and vice versa. Okay. And then you keep going you keep repeating that, except that the first subdomain maintains its own solution on the first subdomain, and the second subdomain, its own solution is maintained. In other words, we never try to construct a global solution, which is, we never have to agree on what is a solution in the overlap region. Okay? So it's slightly different than what I wrote over here. Right? What I wrote over here is that we're going to take the average, and that's going to be the solution over here, and that's going to affect the solution at the next step, because that's going to change the values on these internal interfaces. Okay? But if we don't take the average, we have separate solutions in the two regions, omega 1 and omega 2, then we actually will see that the convergence is faster. Okay? And we hope that when we take many steps, the method converges, and the solution in the overlap region converges. The solution for the first subdomain and the solution for the second subdomain, they converge in the overlap region. Okay, so this method, which is really only understood after 2000. This is why this book doesn't talk about that method. Okay, this method, I'm not sure what is the best name for it, because people are still, I don't know if there's agreement about the best name. But these authors in this first book call it the Jacobi-Schwarz method, and that's what I'm going to call it as well. So this is a parallel method. Okay. So unlike before, we're going to solve the subproblems in parallel. And the algorithm, like before, start with an initial guess. Call it U0. We're going to loop like before. And we're going to solve a subproblem in the first subdomain. And what I'm going to do differently is I'm going to put a subscript on the U. Okay? And I'm going to have a subscript on the second subdomain, U1 and U2. And U1 and U2 are functions that can overlap because they overlap in space. Their domains overlap. Okay? But they don't have to be the same. And in contrast to what we wrote before, we had a single global function U in this procedure. So we had some single global function. Here we don't have a single global function. So this is equal to F in the first subdomain, U1 equals 0 on the boundary. So these are all the same. U1 is equal to U it's going to be, we're going to take the boundary information from the other subdomain. Okay. Gamma 1. So this is, I'm going to call this n plus 1 because we're done. Okay. We're done with the first subdomain. We're not going to correct it again. And then the second problem, U2 equals F. The second subdomain, U2 equals 0 on the boundary. and U2 is equal to U1 on gamma 2. And here we're going to have n plus 1. Okay. And what value of U1 do we use here? We don't use this one because this hasn't been computed yet. We're doing these in parallel, so this is n. Okay, so in particular, I'm going to circle it so that you notice that that has some significance. All right, and then end loop. So we have these two subproblems which are performed in parallel. So we'll say note U1 and U2 are local solutions okay, that generally do not agree in the overlap region. However, we hope that the method converges so that the solutions U1 and U2 in the overlap region are the same. Okay? So let's look at the, yes?
U1 n plus 1 equal to 0 under omega 1. Yeah. Here contain the gamma 1.
No. So let me add that note. So omega 1, so omega I does not include the boundary or gamma I. Does that make sense? That's a good point to clarify things.
Means that if in the this here the boundary is set gamma 1 and this here is container.
Oh, sorry. I do need that. I thought you meant something else. Yeah, so that's a typo. So that's a typo. But going back to here, this is maybe something you assumed already, which I may have even mentioned yesterday. It's also the same case as yesterday. Okay, thanks for that correction. All right, so now we'll go and look at the discrete versions of these problems. So this is the continuous version, and we're going to talk about the discrete version of the alternating Schwartz method first. Yep. Sure.
This is, for example, to average the overlapping part. So that you take care of more than just, this one's just a boundary.
Yeah, so averaging seems to make things worse, right? So suppose your two subproblems are very different, so you don't want to average.
Yeah. So how about in the later stage? I mean, usually this one, the final solution is sort of continuous. So if it's a later stage, in the
would averaging not? Yeah, averaging probably doesn't matter so much in a later stage, but maybe it still does. I don't know, because it's all relative. right? You're trying to resolve the errors more accurately in the later stage as well.
In this Jacobi Schwarz method, you sort of you just control the boundary, right? And so how does convergence of this Jacobi Schwarz, is that good or?
It is, so there's another method which you may have heard of called Additive Schwarz.
Yeah.
We're going to talk about Additive Schwarz as well. But Additive Schwarz is not the discrete version of Jacobi Schwarz. Okay, so in the history of domain decomposition methods, there was alternating Schwartz, and then a discrete version of alternating Schwartz, which we're going to talk about right now, called multiplicative Schwartz. And then from this discrete multiplicative Schwartz, we could also come up with a parallel algorithm that is called Additive Schwarz. But Additive Schwarz is not derived from a differential problem. Okay, so that's why it's important to look at what is the differential method on the differential problem and define the method. So Additive Schwarz is a really lousy method. Let's say it hardly converges. Okay, so it's generally, it hardly converges by itself. So it's actually only used as a preconditioner. Then a method related to Additive Schwarz was discovered, actually by accident. This method is called the restricted Additive Schwarz method. You may have heard of that. Restricted Additive Schwarz is a very nice method. And it turns out to be the discrete version of Jacobi Schwarz. Okay, in restricted Additive Schwarz, each processor holds on to the local solution without trying to average the solutions in the subdomains. Okay? So restricted Additive Schwarz was discovered in 1999, and that's why this earlier book doesn't talk about this. So a lot of these books before 1999 will follow the standard procedure of explaining alternating Schwarz, introducing the discrete version, which is called multiplicative Schwarz, then additive Schwarz, and then we're done. But really, this is, I think, the modern treatment, which is show alternating Schwarz in the differential case, show Jacobi Schwarz in the differential case, and then show multiplicative Schwarz, which is the discrete version of this, right? And then show restricted additive Schwarz, which is the discrete version of this. But then also talk about additive Schwarz, which can only really be derived from the multiplicative Schwarz. On the other hand, you can try to write down a differential, method at the continuous level for additive Schwarz. And people have done that, although I don't know how natural it feels. But it is possible to go backwards and say, well, this is the algebraic method. What would be the method at the continuous level? So that is possible. But I'm not going to take that step. Okay? So let's look at the discrete viewpoint. And I'm going to talk about the alternating Schwarz for alternating Schwarz. And I'm going to do a one-dimensional problem, my favorite one-dimensional problem. And it should be very clear how alternating Schwarz works. And in fact, later on, I'll show you a demo of how it works in MATLAB. Okay, so let's consider this problem. This is the domain, and we have Dirichlet boundary conditions set to 0 at the two ends, right? So that corresponds to these Dirichlet conditions at the two ends. I'm going to label these 0, 1, 2, 3, 4, 5, 6. I think this is the same problem we did yesterday. I don't know if we have exactly the same number of nodes, but we did this problem yesterday, but for the non-overlapping case. And then now we're going to have two overlapping subdomains. So the first overlapping subdomain, the first subdomain is going to be this one. Okay? And I'm going to assume for simplicity, since we have zero Dirichlet conditions, that I'm just going to remove these from the matrix. Right? So I'm going to just ignore these points and these points 0 and 6. So this is the first subdomain, and then the second subdomain is this one. Okay, so you can see that the subdomains overlap. Okay, so in the first subdomain, this is gamma 1. Okay, and in the second subdomain, this is gamma 2. Okay, and you can see that there is a variable, let's call it U3. U3 is in both subdomains. Okay, so U3 is a variable that lives on the inside over here. Okay, and we have some variables U1, which is only in the first subdomain, and U5, which is only in the second subdomain. Okay. So if we write down the matrix for this problem, so the discrete problem is A, U equals F. This is a 5 by 5 matrix. We assume we've taken care of the boundaries on the Dirichlet boundaries. And A is this matrix with 2's on the diagonal and minus 1's on the off diagonal. Okay, so that's A. And we have U. Let me just write A, U equals F. A, U, U1 up to U5 equals F, F1 up to F5. Okay, so this is the global problem. Now I'm going to write down the two subproblems for alternating Schwartz. So for the first subdomain, the problem is there are 4 points, right? There are 4 points of interest. The pink subdomain. So that's the matrix, the 4 points of interest, U1, U2, U3, U4. F1, F2, F3, F4. And the matrix is 2, minus 1, minus 1, 2, minus 1, minus 1, 2, minus 1. And then I'm going to put a 1 over here, right? Because the value of U4 is known. And the value of U4 is not F4. It is whatever, I'm going to call it alpha. And I'm going to say that alpha is equal to U4, the current value of U4. Okay? So the first 3 equations help us define U1, U2, and U3. And U4, this boundary value, is equal to alpha, which is whatever in the very first iteration, it's going to be U4 of the initial guess. U4 of the initial guess. And I'm just going to call that alpha over here. And we can just make this matrix equation simpler by eliminating U4. So we're just going to have 2, 2, 2 with minus 1s. Here's the U. And then F1, F2, and then what should be over here? It's F3. And then we're going to move this known value of alpha to the other side. So F3 plus alpha. Okay? So that's the equation that we're going to need to solve in the first subdomain. Okay, it's always going to be the same equations, but alpha is going to change, right? Because it's going to be taken from the solution on the other side. And then for the second subdomain, and I'm going to do this in a slightly different order. So what are the variables of interest? U2, U3, U4, U5. F1, I'm going to say F3, F4, F5. So U2 is the known boundary value. I'm going to put a 1 here. And the other equations from the discretization look like that. And I'm going to call this beta. And beta is equal to U2, the current value of U2. Right? And I can simplify this like I did above. 2, 2, 2. Minus 1 on the off diagonals, U3, U4, U5 equals. So in the first, for the equation for U3, I'm going to move the known value to the right-hand side. So that's F3 plus beta, F4, F5. Okay. And I'm going to show you this in MATLAB. So I'm going to basically run this in MATLAB, and we'll see how fast it converges. Okay, so now that we've seen the matrices, let's try to write some symbols. So matrix, write down the algebraic view. So notice these matrices, these 3 by 3 matrices. There's one over here. There's one over here. And these are just parts of this matrix. Here is the first one for the first subdomain. And for the second subdomain, we have this one. So we had overlapping subdomains, and here the matrix, the blocks of the matrix overlap. And all of the non-zeros are within the overlapping blocks. There are no non-zeros outside of the overlapping blocks. Okay, so I'm going to call these matrices, I'm going to call this matrix A omega 1. And I'm going to call this matrix A omega 2. Okay, and A omega 1 and A omega 2 overlap. And similarly, I can define the variables u on omega 1 and u on omega 2, and those variables overlap. Okay, there are components in those two vectors that overlap. And now let's write down these two equations. So these are the matrices. Let's write down the two equations. So A omega 1 times u omega 1. Okay, so that's A omega 1 times u omega 1 equals, and that's going to be okay, so I want to write f omega 1, but f does not include the alpha. Okay, so I'm going to need this thing over here as well. Okay, so that part of the matrix I'm going to call A gamma 1. Okay, so this part of the matrix A omega 1, that's A gamma 1. That will be multiplied by U gamma 1. And that's going to be equal to F omega 1. Okay? So to be really clear, U omega 1 contains U 1 to 3. And U gamma 1 is just U 4 in this example. And for the second equation, for the second subdomain, we have A omega 2 U omega 2 plus A gamma 2 U gamma 2 equals F omega 1. I guess I should have used red over here because that's for the first subdomain. For the second subdomain, what are the variables in U omega 2? So this is just U 3 to 5. And this is just U 2. Okay. All right, so now we have these two equations. How do we solve them? Okay, we're going to solve them one after another. Okay, so let's write down some iterates. We're going to use superscripts. I'll use pink again for those. So in the first equation, we're going to try to solve for U omega 1. Okay, so at iteration n, okay, we're going to try to solve that using boundary values that were computed previously. And if you didn't compute it previously, then from the initial guess. So this is at level n. Okay, and for u at omega 2, this is n plus 1. Okay. Using boundary values that were computed previously. So this is also n plus 1. Okay. Now this is a little bit weird because there are some, because these sets u omega 1 and u omega 2, they overlap. Okay, so there are some variables that were computed here that will overwrite some other variable. So it's a little bit, I wanted to point out that little bit of trickiness. So let's move we could rewrite this a little bit. I think I'll probably need more space over here. We can rewrite this by moving these two second terms to the right-hand side, okay, and then adding another term, which I'll show you in a moment. And that's going to give us, I wonder if I should skip a step. Okay, let me skip a step. So U gamma 1 equals U gamma 1 plus A gamma 1 inverse F gamma 1 minus A gamma 1 U gamma 1 minus A, sorry, those were omegas. Okay. So I rewrote the first equation. I haven't put the superscripts. I haven't put the iterations on yet. And then for the second equation, U omega 2 plus A omega 2 inverse F omega 2 minus A omega 2 U omega 2 minus A omega 2 A gamma 2 U gamma 2. Okay. So if you ignore the pink, right, I've just rewritten the top and the bottom. I'm moving these to the right-hand side. And then I've added a term. I've added A omega 1 times U omega 1 onto both sides over here, and the corresponding term on both sides over here, so that what is in brackets looks like a residual. Okay, so in brackets, this looks like a residual. If you look at this equation, if you write down the residual, that's F minus these two terms, right? So F minus these two terms, that looks like a residual, right? And now we'll put these iteration counts back on. That's n plus 1. This is n. We've added this new thing that comes from n, right? And then this was at level n, and this was at level n plus 1. And this is n plus 1. Okay? So this is a method that we call multiplicative Schwarz. I'm going to write it in a slightly different form. This form is a little bit difficult to use for two reasons. One is this residual contains components of U at different levels, at different iteration counts. So it's a little bit difficult. And also there's some overwriting of these components. Okay, both over here and over here. Okay. So I'll write it in a simpler form. So written more simply, two sets of equations. Okay, so now U, I'm not going to distinguish. So U is this is multiplicative, so I actually don't have to distinguish. So this is the global U at the n plus a half step. So that is computed by updating the previous value and solving with a omega 1, okay, but ignoring what happens in the other parts of the domain, applied to the residual f minus au at level n. Okay, so the first equation is equivalent to that. And then the second equation okay, so we're going to update the previous solution. So this is done first. This is update the previous solution plus ignore what happens on the first subdomain and solve in the second subdomain using the residual that was just computed based on the solution in the first part. Okay? So this is called the multiplicative Schwartz. So this is called the multiplicative Schwartz method. And it looks a lot like a stationary iteration, right? We have a residual and we have some kind of preconditioner, you can say. Actually, it's over, I should write it in, you'll see how it's written, what the preconditioner actually is later on. But this is like A inverse times the residual, which is the correction to some initial value, right? So algebraically, we saw this method from the differential side. Algebraically, it looks like a common iteration. Okay, so how can we parallelize this? And the parallel version of these two equations is called Additive Schwarz. So as I said earlier, Additive Schwarz was just derived from Multiplicative Schwarz by trying to make this a parallel method. Here, we do one and then the other, and then one and then the other. Additive Schwarz, we're going to try to do both of them together. It's not going to turn out to be the same as Jacobi Schwarz. So the Additive Schwarz okay, so that's this. I'm going to try to do both at the same time. U n plus a half equals un plus this thing over here times the residual. So the first step doesn't look any different. And then the second step okay. Since we're doing it at the same time, we don't have this available. So this will also be un. Okay. Plus this thing now. And since we're doing it at the same time, we don't have an updated residual. We still have the same residual here. Okay. So this is the Additive Schwarz method. It can be written perhaps in one step. Un plus 1 equals un plus these two things together times the residual Okay? And this is why it's called additive Schwarz. We've added these two operators together. Okay? Remember, they kind of overlap. And this is, and multiplicative Schwarz, the effect is to multiply in sequence by these two operators. So some important notes about additive Schwarz. Not the discrete version of Jacobi Schwartz. So point 1, and then point 2 does not converge in general by itself. This is a fact of life that when you try to make things parallel, somehow some other thing is worse. And we saw a little bit of this before, in which we try to use parallel orderings, but the parallel orderings make things a little bit worse. So it does not converge in general. So it's often used as a preconditioner. So the a preconditioning operator doesn't have to converge. It just needs to reduce the residual by a little bit. Okay. So used as a preconditioner. Okay. Let me show you one other thing. Some notation that really helps simplify the understanding and also perhaps the implementation of some of these methods. So let's define Ri as a type of restriction operator. So remember, we saw restriction in multigrid. It maps some set of variables to some smaller set of variables. So Ri as the restriction operator from all of the variables to the variables in omega I. In other words, u omega I is equal to Ri times u. Okay, so we have all of the variables, a long vector, apply the restriction operator, and we get a shorter vector only containing the variables in the ith subdomain. If we use this notation, then multiplicative Schwarz can be written as, so I'm just going to write down these equations over here. These equations over here. So un plus a half equals un plus, okay, I'm going to take the residual, and I don't want to apply all of the, I don't want to apply it to this, I only want to apply some components of this residual to that operator, this block. And I only need to take out some of the, we don't need all of the columns here, all of the rows here, we just need some of the rows. Okay? So I have the residual f minus au at level n. So we're going to restrict that to the variables in the first subdomain. Then we're going to apply A omega 1 inverse. And A omega 1 inverse can be written itself as Ri A Ri transpose. Just like we had in multigrid, the Galerkin coarse grid approximation, this is taking our original matrix A taking out the block of A that we want, and then computing the inverse. Okay? And then we're going to, okay, so actually we do need all of the rows. So now we're going to we're going to interpolate. So just the transpose of restriction, we're going to interpolate onto all of the variables so that we can add to a vector that contains all of the variables. So this looks like a coarse grid correction like before, except that these R's are not the restriction operators that we're used to, transposes of let's say, linear interpolation. But these R's are just matrices containing 0 and 1 that select out the components of the subdomain variables that we want. Okay, and similarly we have for un plus 1 plus r. So I use ri's over here. These could be 1s because that's the first step. So now we have 2 as the first step, as the second step. Okay, and further, if we define bi, since all of these are repeated, let's define bi as ri transpose ri a ri transpose inverse ri. Then we can write these two steps as a single step. Un plus 1 is equal to un plus b1 plus b2 plus b2 a b1 f minus a u at level n. Okay, so now we've combined these two into a single equation, and it looks like correcting the previous approximation with this correction, something times the residual. So this is the preconditioner. We have to solve with this matrix, which is the preconditioner. We can think of that as a preconditioner. And if we do the exactly same thing for additive Schwarz, we would have un plus 1 equals un plus b1 plus b2 f minus a u at level n. Okay? All right, so I'm going to use the screen now. Thank you. Okay, so I have this file which I'm going to post after class. It's called Schwartz.m, and it contains a number of examples. I think 4 examples for the very simple problem with the 5 variables, the 1D problem. Okay, so I'm going to generate this Laplacian with 5 variables, a one-dimensional Laplacian. And here are the capital A i's, right? So these are the 3x3 subblocks that you saw before. Okay, and I'm going to use the same f for all of the problems. I'm going to generate the same right-hand side, so the solutions should be the same for the different methods. And here's my very first implementation of multiplicative Schwartz. The initial approximation is 0. Okay, and then I'm going to take a number of iterations. I'm going to take 10 iterations. Okay, and for each subproblem, I'm going to have a right-hand side. And this is the value of the boundary, the Dirichlet condition, for in the other subdomain, right? So its value initially is going to be 0. And then I'm going to solve for this local problem, and I'm going to immediately write the result into the global solution U. Okay, so that's the solution on the first subproblem. It's exactly the equations that I wrote down on the board. So you can compare what we wrote on the board to these equations. And then this is the second half, right? So this is the boundary value at 2 incorporated into the right-hand side, right? And then solve the second problem. And I'm going to, after each iteration, I'm going to print the norm of the global solution. So this is multiplicative Schwartz. Okay. I have a second implementation of multiplicative Schwartz, a much shorter one, and that uses the fact that multiplicative Schwartz is equivalent to this overlapping Gauss-Seidel type of method that we just saw. So it has, we compute a residual. So what I'm going to do is I start again with an initial guess that is 0. And I'm going to have an operator. Is it still on the board? So I'm going to define this thing in brackets as A1 and this thing in brackets as A2. Right? So it's a 0 matrix except for the 3x3 block in the top left corner. That's the inverse of A, which is that 3x3 matrix. And then A2, which is a 0 matrix except in the, most of you can't see this, but in the lower right corner, the 3x3 matrix, which is the inverse of A as well. Then I'm going to take 10 iterations like before. I'm going to compute the residual, and I'm going to take one standard step using A1 and update the residual, then compute another standard step using A2. Okay, and I'm going to print the residuals after each step. And this is exactly the same method, so the iterates should be exactly the same. Okay, and now we'll look at additive Schwartz. So additive Schwartz, start with initial guess, exactly the same operators A1 and A2, right? But instead of doing them in sequence, like the Gauss-Seidel method, I'm going to do it in parallel, like the Jacobi method. So here the A1 and A2 are added together and applied to the residual. Okay? We'll see how that converges. And then restricted additive Schwartz. Okay, so compare this to the multiplicative version. Okay, so we have a global solution U, and in this implementation I'm going to have a U1, which is the local solution on U1 that I'm maintaining, okay, and a local solution U2 that I'm maintaining. And I'm only going to use components 1 to 3 of this U1 and components 3 to 5 of U2. So those are private copies of the solution. And on U3, this overlap component, they're not going to generally agree. Okay? So here I'm going to solve the first problem. So this was exactly the same as before. But instead of writing the solution back to the global U, I'm just going to store it locally. Okay? And here is the second subproblem. Okay? But instead of the updated value of U1, I'm going to use an old value of U1. Okay? So this comes from the other subdomain. And I'm going to use the other value. In fact, do I need to do this for U2? Okay, so U2 is okay because I'm going to get the new value after I compute the global solution. So in general, there is no global solution. But in order to compute a residual over here, I'm going to need a global solution. And for that, I'm just going to compute the average of the two values. So I'm just going to add them together, and where they overlap, I'm going to divide by 2. Okay? So let's see how that works. Okay. So here is the first implementation of multiplicative Schwartz. These are the residuals. You can see that they're converging. Okay, it's a very small problem. 10 steps is maybe a lot for this small problem. And then for the second implementation of multiplicative Schwartz, you can see that the iterates are exactly the same. So it shows that the implementations are equivalent. And then for additive Schwartz, you can see that the convergence is not good. Okay, so additive Schwartz is a lousy method, even for this very simple problem, like a 1D Laplacian problem. It can't even work on that. Okay? And then for restricted additive Schwartz, a parallel method, which is better than additive Schwartz, you can see that it does converge. So after 10 steps, it goes down to about 10 to the minus 3 in terms of residual. It's about half as fast as multiplicative Schwartz, which is what you might expect. This is a parallel method. Multiplicative Schwartz is not a parallel method. Okay? So let me give you a simple exercise to do for next class. So here's the exercise. So the exercise is simply to modify the multiplicative Schwartz code in the Schwartz.m file. So that you can do a larger problem. So I did a 5 by 5 problem. So a larger 1D problem. Okay, so we're going to stick with 1D. And I did 5 points. So your input should be n, which is the number of grid points in the problem. And then also n1 and n2, which is the number of points in the first subdomain, n2 number of points in the second subdomain, and n1 plus n2 should be greater than n so that we have some overlap. And try different values of n1 and n2 to use larger amounts of overlap or smaller amounts of overlap to see how the amount of overlap affects the convergence. And you can probably guess that if there's a lot of overlap, convergence will be faster. And if there is a little bit of overlap, convergence will be slower. All right? Are there any questions? Okay, if not, have a good day, and I'll see you tomorrow.